We were doing center of mass and system of particles. What is the last topic that we did?
Center of mass completed, sir.
Center of mass completed. Okay. So now we have to start the system of particles, right? Uh, Means that rotational motion. One minute. Okay. So now we will start the basics of rotational motion. Till now we have not started the rotational motion. I think we started, no, rotational motion.
Meeting ended, sir. That's right.
Sorry.
In while discussing on the meeting ended, sir. Can start from starting. Just in the definition, the difference between rotation and translation.
Okay. Okay, and what about the angular variables? We introduced the angular variable, angular displacement. Yeah, we
Yeah, not
discussed. Not discussed?
not discussed, sir.
Okay. Okay. So I'm sharing it. So I have shared the screen. Is it visible to you? Screen is visible, right?
Visible, sir. Visible, sir.
Okay, so we were discussing the translational and rotational. So translational motion is one in which when a body moves from one place to another place, actually all the particles of the body have the same displacement. All the particles follow same type of path, and all the particles have same velocity at any instant and same acceleration. For example, here you can see. So when this body is going from here to here, and it is going from here to here, and at every instant, velocity of all the particles of the body is same. And acceleration at all the instant is same, and the distance and displacement covered by all the particles are exactly same. So this happens in translational motion. Now in rotational motion, this is not true. In rotational motion, different particles of the body can have different velocity. For example, you can see here this particle may be at this instant going in this direction, whereas at this instant it is going in this direction. See the Hannah? That is not the correct way. Actually, what I'm trying to say is that it may be possible that the different particles of the body are going in the different direction at the same time. And that's why orientation of the body is changing. You can see if a line is drawn on the body, look at the orientation of this line is changing. This line is rotating because the whole body is rotating. If a body is doing translational motion, then you will not see this. Means any line drawn on the body will not be change its orientation. Let's go to the next. For example, here you can see rotation about a fixed axis. For example, rotation of fan, ceiling fan. So here you can see that in case of rotation about a fixed axis, you can see all the particles of the body goes in a circular path, and center of all the circle lie on an imaginary line which we call as the axis of rotation. Rotation about fixed axis means all the particles goes in a circle of fixed radius. Radius of that circle will not change because it is a rigid body and it is rotating about a fixed axis. Center of all the circular path of the particle, all the particles lie on the same line, which is called as the axis of rotation. In case of rotation about fixed axis, all the particle goes in a circle, and this is also called as pure rotation. Now, to understand the motion of rigid body, we'll have to introduce some angular variables. Here you can easily see that there is a rod, and this rod is hinged about a point. This is the rod you can see here. This is the rod, and this rod can rotate because it is hinged about this. So it can rotate like this if you will release it. See, when you released it, see now the current position of the rod is this. Okay, so it goes down by some distance. So from its initial position, which was this was its initial position, the entire rod actually rotated by some angle. This angle, that the body rotates in a given interval of time, that you can call as its angular displacement. So here you can see angular displacement is simply, you can say that in rotational motion, angular displacement is the angle rotated by the radius vector of a particle, of any particle you can take, because it is a rigid body. So when the body rotates, all particle goes in circle in any interval of time. Angular displacement of all the particle is same in a rigid body. Rotation about fixed axis. We are only talking about rigid body rotation about fixed axis. So in that case, by how much angular displacement of a particle of the body is changing, by how much angle the position vector of a particle is rotating, that is called as its angular displacement.
That means here we can say that it's the same as circular motion only. So, but here we are considering all the definitions for a body now, sir.
Yeah, yes.
The body means any particle we can consider also these definitions for any particle in a body.
Any particle, because it is a rigid body. So if whole body rotates, all the particle goes in circle. In any interval of time, angular displacement of all the particle will be same. We are especially talking about a fixed axis. So about a fixed axis, if a body rotates, angular displacement of all the particle is same, and that is nothing but angular displacement of the body. So the angle by which position vector of any particle with respect to the axis rotates, that is the angular displacement of the body. Now, angular velocity. Angular velocity is simply the rate at which the angular displacement is taking place. So, in unit time, how much angular displacement? That is the average angular velocity. And instantaneous is simply the rate of change of angular displacement. So, d theta by dt. Its unit will be radian per second. And the unit of angular displacement you already know will be a radian. Now in the vector form, you already know from circular motion that v vector is equal to omega vector cross r vector, not r vector cross omega vector. Okay, it is always omega vector cross r vector. This is the relationship between linear velocity of a particle, angular velocity of vector of the body, and position vector of that particle of the body. Just like circular motion, because in pure rotation about a fixed axis, all particles of the body are doing circular motion. That's why everything is similar to circular motion. Now, angular acceleration. So, angular acceleration of a rotating body is the rate of change of angular velocity. That's it. Angular acceleration is rate of change of angular velocity. Average angular acceleration will be change in angular velocity by time, and instantaneous will be, you know, by differentiation you will get d omega by dt. Its unit will be radian per second square, radian per second square. Okay. If suppose a body rotates with a constant angular velocity, then angular acceleration will be zero. So whether it is circular or rotational motion with constant angular velocity, then angular acceleration will be zero. Average angular acceleration is simply change in velocity upon time. Change in angular velocity upon time. Again, here you can see that there is a relationship between the linear acceleration of a particle and angular acceleration of the body. So again, linear, but here you have to understand that when I say linear, there are two linear acceleration. So this is actually the, for example, suppose this is a rigid body and the body is rotating about an axis passing through it like this. This is the axis. So if there is a particle here, let's say, when the body rotates like this, when the body rotates like this particle will be going in a circle. Are you getting? So when this particle is going in a circle, let's say position vector of the particle is, let's say, some r vector. So let's say that this is the particle whose position vector is r vector. Particle whose position vector is r vector. This is position vector. And if it is rotating with a constant angular acceleration alpha, so this particle here will have a tangential acceleration as well as it will have a tangential acceleration. You can clearly see will be along the tangent to this circular path, which I think will come in the backward direction. So you have to imagine in 3D, it will go in backward direction, not in the plane. You can visualize this, okay? And its magnitude is nothing but r alpha. Magnitude is r alpha, but in vector form, you know, this a
This is due
tangential
to
vector.
change in direction, sir, this acceleration.
Sorry,
Sir, this acceleration tangent is due to change in direction of velocity.
no, you already know that in circular motion we studied.
I mean, asking in here also such 3 dimensions.
So it is due to, you know that, you know the answer. Tell me.
The change in direction.
Okay. And what is other than tangential? What other acceleration is there?
Centripetal, no, sir.
Okay. And centripetal is due to?
Sorry.
You already know that these things.
Yes, sir.
So if you already know, then don't waste time. Okay. So now here you can see these are the equations of motion. So in linear motion, you use these equations when Linear acceleration is constant. Okay. And in angular motion, you again use these equations when angular acceleration is constant. You already know all this, right?
Circular motion.
Again, these are the kinematic equations which you can use as it is for rotational motion also here. Just see the equations for rotational motion. Do you understand this? Or you have doubt in any one of this? Linear you already studied in kinematics. Now look about the rotation. Okay, understood.
Understood.
Now there is rigid body constraints. So you already know that because it is a rigid body, here you can see it is a rigid body. Whatever the body will do, body will rotate or body will translate, the separation between the two body will never change. So whatever is the velocity of this body, whatever is the velocity of this particle along the line joining, same will be velocity of this particle along the line joining them. Because if it is not same, then separation between them will change. So here you got a relationship that okay, its component will be VA cos, let's say this angle is theta A. So VA cos theta A, and here you are getting VB cos theta B.
Sir, here can we say, sir, that uh, sir, vertical components can be also equal, sir, because can we say, sir, like that?
You know it, you know the answer.
Yes, sir. Then.
You know that it will not be equal. Are you getting? So if you know something, don't ask it. I know that you know it. So we are not talking about vertical component, we are talking about the component of the velocity along the line joining them. Vertical components can change. Vertical component cannot change means this component can also means vertical component can be different. Their vertical component can be different. Now with respect to one particle, if you suppose sit at one particle and you look at another particle, it can only do circular motion. Means with respect to one particle, other particle can only do circular motion because separation between them cannot change. So if separation between the two particles cannot change, only possibility is that with respect to one particle, another particle can move keeping the separation constant. So the only possibility is circular motion. So with respect to particle A, particle B will be going in a circle. And you know in circular motion, velocity is always perpendicular to the perpendicular to the radius. So if you are sitting at A, particle B will be moving in a center, in a circle with its center at A. So AB became the radius, and now this is the relative velocity perpendicular component. Means there will be no relative velocity along the component along the line joining them because relative velocity along the line joining them will be zero. But there will be relative velocity in the perpendicular direction to AB. If you want, you can also find the angular velocity of this body. So angular velocity of the body, you can write that the angular velocity of B with respect to A. You can write that okay, that is equal to its relative velocity of B with respect to A, and this relative velocity will be in the perpendicular components upon the radius, which is AB. Let's say AB is L, so upon L. Tell me, you have any doubt, you can ask.
No doubt.
Okay. Okay, so now the next important thing that we have to start, the first most important thing in the study of the rotational motion is about the moment of inertia. Here you have to understand that moment of inertia plays exactly the same role in rotational motion as the inertia plays in the translational motion. Now you have to understand that inertia in translational motion, inertia depends on mass. And in place of inertia here in rotational motion, there is a quantity called as moment of inertia having the same role. Means inertia is a property which opposes any change in its state of motion that we already studied. Similarly, moment of inertia is also a quantity which which is actually a property which opposes, you know, due to which a body opposes any change in its state of rest or uniform rotation. So if a body is at rest, because of moment of inertia, it want to stay at rest. So it will not by its own start rotating because of the moment of inertia. On the other hand, there is a if there is a mm, uh, if there is a body which is in uniform rotation, then because of this property, moment of inertia, the body will continue rotating. It will oppose any change. So because it opposes any change in its state, so change cannot take place without any external agent. An external agent is required to change the state of rest or the state of uniform rotation. So if something is at rest and you have to rotate it, there will be it can happen only due to some external agent. And if something is rotating and it has to stop, then also there should be some external agent. Now let's come to moment of inertia. So try to relate it with inertia. In translational motion, we already studied that inertia was given concept given by the Galileo. So inertia depend on mass, but here you can see that moment of inertia depends on mass as well as perpendicular distance of the mass from the axis of rotation. Here you can see this diagram. So if you will see, look at this diagram, you'll see that there is an axis and there are few particles of masses m1, m2, m3, and they are at some perpendicular distance. So if there is a particle m1, another particle m2, another particle m3 at some perpendicular distance r1, r2, r3 from the axis, they are capable of rotating about this axis. So then moment of inertia of this system of particles can be defined as, so mathematically it is defined as that moment of inertia I is equal to summation of mr square, where m is mass of the particle and r is the, you can say, the perpendicular distance from the axis. 1 minute. Huh? Okay, leave it. So summation m r square, where m is mass of the particle and r is the perpendicular distance of the particle from the axis. Okay. And if there are multiple discrete particles, then you will simply do the summation from I equal to 1 to n all the particles. Okay. So finally you will get this. Finally you will get this formula. Okay. Now, instead of discrete particle, there can be a single body rotating about an axis. And you know that a body is also not but a collection of particles. So for example, if here you can see that there is a body and this body is rotating about an axis, you can see that this is the axis through which the body is, about which the body is rotating. Now you can see the entire body. We can consider that this is nothing but a collection of system of particle. So you can take a very small region in the body, or you can say that you can take an element of a very small mass dm at a distance r. Another element is very small, so you can ignore the size of the element because it is very, very, very small. A small volume where delta v tends to zero, that small volume at a distance r. So now because this is very, very small, you can consider it as a single particle of mass m. Okay. And then you can apply the same formula. But because here distribution is continuous, so in case of continuous distribution, we don't use summation. We use integration. So mass is distributed everywhere at all the distances from the axis. So that is called as continuous distribution. So now you will just do the integration of
Sir, integration
r.
and summation both are same only, no, sir.
Same thing, yes. But the difference is that summation we do for discrete distribution. For example, here is a mass and here is no mass. Here is no mass. Here is no mass. Again, here is the mass. Again, here another mass. Are you getting? So there are certain distances where mass is not there. But here, that is not the case. Here, everywhere mass is there. Here also, here also, here also, here also, here also. So for continuous distribution, you do integration. Are you getting? For example, in this region, is there any mass here? No. Here is the mass, right? And then directly here is the mass. And then directly here is the mass. So this is discrete. Means lump of masses are there at certain distances. But here, in case of a body, it is continuous distribution. Means, you know, you can see that the mass is everywhere. Here is also mass, here is also mass, here is also mass, here is also, here also, here also, here also, here also, here also, everywhere, right? Continuous is there, mass. That is not the case here. Here no mass, here no mass, here no mass, no mass. Only mass is here. So that is discrete. So summation we use for discrete. But when it is continuous distribution, at all the distances from the axis, there is mass. All the distances does not mean that, yeah, in a certain region, in this region, at all distance there is mass. There is no distance where there is no mass in this region. But here in this region, if you take, there are many points when there is no mass. Are you getting? So you cannot do the integration here. Here you can do the integration. But the idea is same, both are adding. One is continuous addition, one is discrete addition. For example, if you have to add n natural number, you will do summation. But it is discrete. Because between n natural number, there are infinite rational, irrational, real numbers. Are you getting? So that is not continuous. Now, moment of inertia. So as you understood that, okay, it is summation of mr square. where m is mass and r is the perpendicular distance of that mass from the axis. A square of the perpendicular distance you will take, so r square dm. So then you already know its dimension will be dimension of mass and dimension of distance is square, no time dimension, so ml square. Its unit will be kg meter square, simple. Now here you have to understand that moment of inertia does not depend on mass only. It depends on mass, total mass, as well as distribution of mass about the axis of rotation. It also depends on the position of the axis of rotation. That's why I said distribution of mass about the axis of rotation. So if you change the axis of rotation, then distribution of mass about the axis of rotation will change and moment of inertia will change. Moment of inertia has nothing to do with the body is rotating, not rotating, angular velocity, torque, angular velocity. No. Only depends on mass and distribution of mass about the axis. Moment of inertia is not a vector quantity. Some books go to the extent and then say that it is also not a scalar quantity, it is a tensor quantity. But in your JEE syllabus, you don't have to study about the tensor quantity. Only you have to understand that it is not a vector quantity, first of all. And it has, for a same body, moment of inertia has different value about different axes. About different axis of rotation. Now let's try to find the moment of inertia of a rod about an axis passing through center of the rod. So again, same process that we already discussed. Take an element of the rod at a certain distance. I have taken a very small part of the rod at a distance x from the axis. And because it is a rod, so I have taken length of the element as very small length dx. So because this is a very small part of the rod at a distance x, we will take it as a particle. And now you use the formula of moment of inertia for continuous distribution. Again here, what will be mass of the element? So if total mass of the rod is m and total length is L, then mass of the element will be mass of dx length, which is m by L into dx. Moment of inertia of this element only is dmx square. Now dmx square is moment of inertia of the element, which is at a distance x. But we have to find moment of inertia of the entire rod. So we will have to do the summation of moment of inertia of all such elements. So we will integrate it. Sorry.
So we should use the word.
Speak louder. You are not audible.
So here we need to use the word integration also than summation.
Yes, we need to use. But actually, we are doing that. There is no difference actually. But we cannot do this. Actually, we are doing summation also. Here you have to understand that for discrete mass, you cannot do summation, integration. For discrete mass, you cannot do integration. But integration, actually, what you are doing is summation. So, yes, you have to do integration. But in integration, what is happening? Summation of this only for all the terms. So integration is not different from summation, but it can be done for continuous distribution only. So you will do the integration dm x square. And now because the distribution is continuous, you can put limits here. Because mass is present everywhere from minus L by 2 to plus L by 2. That's why you are putting this limit here. Whereas when the mass is discrete, it is not distributed everywhere from minus L by 2 plus L by 2. That's why we cannot do integration. But both is summation only. Integration means actually more than the mathematics, you have to understand actually that what is going on. It is simply addition of all dm r square, dmx square. Addition. Summation, integration, same thing. But yes, you have to do integration. But that integration is nothing but summation only. Okay, so now here you can see that for a ring, you have to find moment of inertia. Again, same thing. See, dm into r square is the moment of inertia. And then you have to do the summation or integration. If you do integration, you will get mr square. Because all the mass is located at the same distance r. So directly you can think that if I will add all dmr square, if I will add all dmr square and r square I am taking common, then it will be simply r square into dm plus dm plus dm, all dm addition will be total mass, right? Okay, so now you have to find the moment of inertia of a disk and think how you will do it. So you have to find the moment of inertia of a disk. Suppose this is a disk. This is a disk, and this is the axis which is passing through center of the disk and perpendicular to the plane of the disk. Imagine it is a disk, and it is given that total mass of this disk is capital M, and also it is given that radius of the disk is, let's say, r. It is given only these two information is given and nothing else. One more information is given, that the mass is distributed uniformly. And now you have to find its moment of inertia about the x. Do it fast. Can you do the derivation following the process? The process that we followed for the rod. Yeah, just like that. You can explain if just follow the same process that we did here. The same process that we did here. First we chose one element, then we calculated moment of inertia of element, then we integrated, means added the moment of inertia of all small elements, all. That is done by a process called as integration.
I'm trying.
Hmm. Whatever theory is given in Narayana material, do you find that that theory is sufficient for all the questions in that book, especially level 5? Is it sufficient, or
No, sir. It's not sufficient, definitely.
you feel it is not sufficient?
It's not sufficient for higher level problems.
Okay.
It is not sufficient, sir. I don't know about new materials, sir.
Okay. I have one material. It is also not new one, but Exactly, I don't know which year is not written. It is the
Mostly
second.
concepts which are not important they will give, sir. Means
Hmm.
generalized problems like that they will mention. Like,
Not in very detail, that sort they will do. Level 5 hint is given or solution also given. Not given.
so only hints will be given, sir. Just one line or two lines.
Okay. Hmm.
Use this concept, this that will be that.
Yeah. Okay, so tell me what you are doing here. How you are selecting the element.
So like a circular ring we can select.
Circular ring you are taking of radius.
So smaller, sir.
Radius small r, and
Mr. Master.
after that what you are doing. Okay, radius is small r, circular ring, then
Sir, I'm finding the mass of the small element, sir.
so you are taking mass of that circular ring as small m, right?
Small DMs lines.
Dm. Okay, dm, then
So then we know moment of inertia will be dm into r square, so due to this small element.
dm into r square. Now what is dm?
So this element mass I'm finding, so means
Okay, what you will substitute in place of, how you will do this integration? So moment of inertia you will say is, will be integration of this, right?
yes, sir.
But then what is dm? How you will substitute that? What you will?
So you can say dm as
Element you have chosen, is it correct? The element that you have chosen. What is your element, first of all?
the ring we cannot consider. I'm considering, sir, as
Okay, ring you are taking. Okay, of radius r. Then what is dm?
so we can take m by 2 pi r. We can take mass per unit. So we can take
M
m
by
by 2
2 pi r. That is totally wrong. You are saying m by
2 pi r plus m dr.
into dr. But when I asked you what is your element, you have not said anything about dr. What is dr?
So then the radius of the ring we can change, the width of that ring.
So there is a ring of width dr, you will say, of a radius r and width dr. Okay, now you can do it. Yes.
Integrating from 0 to r we can do no, sir.
Yeah, so integration 0 to r, and in place of dm you will write it as mass of that ring, which is capital M by, how you will find dm?
The mass per unit length we can take now.
Yeah, how, what
By
equation?
sir, capital M by um, 2 pi r into dr. No, sorry.
No, that is wrong. This is what you are saying, right?
Yes, sir, that is the concept.
That is wrong. Capital M by, you are saying 2 pi r into d, right?
Yes, sir, m by
That is wrong, completely wrong.
mass per unit.
First of all, you have to understand that what is dm? Mass of the
Small
element.
element.
And where is the mass? Which mass you are talking? Where is mass of the element? This mass. This mass, right?
Yes, sir.
This mass has an area. area.
Yes, sir. Means
Mass
mass
of
of
the
the.
disk. Mass of the disk is also distributed in an area, not in a length 2 pi r. Area.
Yes, sir.
So then what you will write?
So then we can check m by pi r square, sir. Pi r square it should
Into,
into dr we can know.
again wrong. Again wrong. This you will write.
2 pi r.
Area.
Yes, sir.
Mass per
Area.
unit area multiplied with area of the string, right?
Yes, sir.
Okay, so similarly, you can find the moment of inertia of a hollow sphere. So now these derivations, idea is same. All the time you have to take element and you have to do the integration. So you must do all these integration by yourself in according to the Narayana book or S.C. Verma book is there. Because then there is only integration. All the cases you have to select the element wisely and do the integration. Now here you can see that in case of a hollow sphere, you will mark a circular arc on the surface of the hollow sphere. Okay, so you draw two radius here at different angle at an angle theta and a theta plus d theta, and then you rotate this radius vector. So this arc will actually draw a ring on the surface of the hollow sphere, and then a ring is formed on the surface of the sphere. This ring will have a width, and that width is nothing but r d theta. And now again the same thing. Again, you know that taking it as a ring, you will find the moment of inertia of the element, and then you will integrate it. Similarly, in case of moment of inertia of a solid sphere, you will take a disk at a distance x of some thickness dx. This is a disk. Now again you will find its mass of the elemental disk, and then use the formula of moment of inertia of the disk, mr square by 2, that is di, and then again integrate. Vary this x from 0 to capital R. That's it. So I think you should do all this derivation, and then you can come with your doubts. Any derivation you are not understanding, that you can come with your doubts. Tell me.
Yes, sir. I will try, sir, everything, and if any doubts, I will ask you guys again.
Yeah. So go through moment of inertia of all, and remember also final result, and then come with. Okay. So now I'm skipping this. All these are derivation. Moment of inertia of a hollow cone. You have to go through it. Mathematics only. Concept is same. Choose one element. Now I'm directly jumping to moment of inertia. Axis theorem. So there are two axis theorem, which is for the calculation of moment of inertia of body. One is called as perpendicular axis theorem, another is called as parallel axis theorem. So let's discuss about first the perpendicular axis theorem. Perpendicular axis theorem, first of all, you have to understand that this theorem is only applicable to plane lamina, means 2D body. Write it down. Perpendicular axis theorem you will not use for a 3D body. You will use this theorem for plane lamina. For 2D body like a rectangular plate, circular plate, you can use it also for a ring. You can use it for for 2D bodies, not for a sphere, not for cone. Are you getting? Not for cylinder. For 3D body, you cannot do. You can only do it for a planar lamina, plain flat 2D bodies. Now this perpendicular axis theorem simply says that if suppose moment of inertia about two axes which are mutually perpendicular and in the plane of the body is, let's say, I1 and I2. So moment of inertia of a body about two axes which are mutually perpendicular and in the plane of the body is, let's say, I1, I2. Then the moment of inertia about a third axis which is perpendicular to the plane of the body and passing through point of intersection of the other two axes is given by I1 plus I2. So moment of inertia about this perpendicular axis, which is the third axis here, you can say that will be nothing but is equal to I1 plus I2. So first of all, I1 and I2 are the moment of inertia of the body about the any two axes which is in the plane of the body, but they should be mutually perpendicular. Then the moment of inertia about the third axis which is perpendicular to the plane of the body means it is perpendicular to both the axes and passing through their point of intersection is equal to I1 plus I2. So that is your perpendicular axis theorem. You can also go through its proof. So the proof is very simple here. You can see that we have taken a disc-like body or any 2D body, any regular, irregular shape, it is applicable, but it should be 2D. And you can see that we have drawn three axes here, two axes in the plane. So you can see this is the first axis passing through the center. This is the second axis passing through center of the body. And this is the third axis, which we have taken perpendicular to both the axis and perpendicular to the plane of the body, passing through point of intersection. And now let's say that the perpendicular distance, let's take one element in the plane of the body. Obviously, element will be in the plane. So take a small element here, dm mass. Now let's say that the perpendicular distance of this element from the x-axis is a, and from this axis, which another axis in the plane, is b. Then clearly moment of inertia about the third axis, if we have to write, here you can see if we have to find moment of inertia about the third axis, which is perpendicular to the plane, then we will take this distance, which is the perpendicular distance of the element from that axis. And now you can clearly see that here one right angle triangle is formed. And in this right angle triangle, you can see this triangle, this R is the hypotenuse, and A and B are the two sides. So if we find moment of inertia about the axis, third axis, which is perpendicular to the plane, it will be dm into r square. And from Pythagoras theorem, you can see r square is a square plus b square. Now it becomes this. Then it separately becomes dm square, dmv square, which is ix plus iy. Tell me, you understood? You have any doubt here? Here you can ask your doubt. Or you understood, then we'll go to next.
Sir, understood, sir. We can go to next.
Okay, so let's go to the next. Then next is parallel axis theorem. So parallel axis theorem, now you have to understand, is applicable for general body, any 2D body, any 3D body, any type of body. So for parallel axis theorem, there is no restriction. So this is any body, even irregular body also. Now parallel axis theorem helps you to find the moment of inertia of a body about an axis which is parallel to the axis passing through center of mass. So first of all, here, suppose that this is center of mass of this whole body, this body. And let's say that this is an axis passing through center of mass of the body. And if the moment of inertia of this body about an axis passing through center of mass is IC, then with the help of parallel axis theorem, you can find moment of inertia about any axis, which is parallel to this axis passing through center of mass. So about any of this axis you can find. Here you have to understand that it is not the center. It is the center of mass. Okay. Again, there is some proof, here also. Okay. So here, because the two axes are parallel, there will be some perpendicular distance between the two axes. Let's call that perpendicular distance as d. So if d is the perpendicular distance between the two body, okay, then if I directly state the moment of inertia of the body about any axis which is parallel to the axis passing through center of mass and at a perpendicular distance d is given by I equal to IC plus md square, where IC is moment of inertia of the whole body about an axis passing through center of mass of the body, plus md square. M is total mass of the body and d is perpendicular distance between the two axes. Is it clear? Tell me.
Yes, sir. It is clear, sir.
Okay. So if it is clear, then you know you can try to find the moment of inertia of the ring and the disk about the different axes. So let's take that this is ring. First of all, this is ring. In case of a ring, let's say mass of the ring is m and radius is r. Let's say these two things are known to you. Mass is m and radius is let's say r is given. So you already know that if mass is m and radius is r, moment of inertia of a ring about an axis passing through center and perpendicular to the plane is mr square, right?
Yes, sir.
Now by using parallel axis theorem, try to find the moment of inertia of the same ring about this axis. Look at this axis. Try. About this axis. It is very simple. You can do it using parallel axis theorem. Why you have to use parallel axis theorem? Because you can here see clearly that the two axes are parallel. The axis which is passing through center of mass and the axis about which you have to find moment of inertia are parallel. So it will be better to use parallel axis theorem. Tell me, you know it.
Yes, sir. Here we can.
Sorry? You can ask your doubt. This and this ring are same ring. You have to find moment of inertia about this axis. Mass of this disk is m. Radius is r. Got the answer, right? Tell me.